Okay, let's get started. So far, what we discussed is the FM generation, FM signal generation. So going back to the basic of FM, what we discussed is the transmission bandwidth of FM signals. Okay, so here's our original message as a simple example. So our message MT is a simple single tone signal, cosine signal, right? This is a simple example. And in this case, if we do the phase modulation, we know that the message should go to the phase part right here, right? Simply, it's going to be like a cosine 2 pi fct, which is carrier, plus phase. And the phase has the message there, right? So this is a phase modulation. However, in frequency modulation, we know that the transmitted signal or modulated signal looks like this. So in the phase part, instead of just message mt, we have integration of m tau, right? In the case of FM. So that's our transmitted signal in FM, right? So when we have this kind of signal, we already learned about the Carson's rule. And this Carson's rule basically tells you that the bandwidth of your FM modulated signal is going to be calculated like this. So in case of PM, you have this transmission bandwidth. And if the FM case, we have this bandwidth. So this one tells you the bandwidth of the signal you transmit. So this signal, this is FM modulated signal. This signal has a different bandwidth. In the earlier amplitude modulation, your bandwidth is still same. Your baseband bandwidth and your the carrier or your the bandpass signal has the same bandwidth, but in this case, that's not the case, right? Your transmitted, your original signal has a single tone. This is your original message, only one frequency. But when you do the FM modulation, this signal, modulated signal, has this much of bandwidth. So your original signal, original message has single frequency, but when you do the FM modulation, your modulated signal has a certain bandwidth, like this much. So that's what we see here. Okay. So if you assume a arbitrary signal, not the single tone, but arbitrary signal, then your signal has your own bandwidth, W. So instead of FM, you can just put it W. Then you can see this is the case. This is the transmission bandwidth of your arbitrary signal. And we call that as a generalized Carson's rule. Right? So we learned about this graph and also this table. So what this table shows you is that depending on the modulation index beta, right, number of significant side frequency changes. So for example, if you have a very low beta, low modulation index, small modulation index, in that case, this one is the same as a narrowband FM. So remember how many significant side frequencies we have in narrowband FM. In narrowband FM, remember that we have two side frequencies, right? For example, one is FC minus FM, the other is FC plus FM. There are only two, right? But if you increase the modulation index, and if the modulation index goes higher, becomes a large value, now we have more and more side frequencies within your bandwidth. You have a more frequency component. So that's what you see here in this graph, right? So you compare the case of beta equal to 1. This is the case of modulation index of 1. The last graph shows you the modulation index of 5. So as the modulation index is getting large, now this is our bandwidth, BT, transmission bandwidth. Within this transmission bandwidth, now you have more side frequencies, right? You have more and more. So that's what you see here in this table. If you have a large modulation index, you have a very large number of side frequencies within your bandwidth. The same thing you can draw in the figure like this. So this one basically tells you the normalized bandwidth. So it's like a BT divided by delta F. But eventually, if your modulation index is getting large, now what happens is your this normalized bandwidth approaches to 2. Why is that? Because your B sub t is approaching to 2 times delta f. 2 times delta f. Why? Because let's go back here. Your transmission bandwidth is 2 times here. See the 2 times delta f. 2 times delta f plus 2 fm. Okay, 2 times delta f plus 2 fm. That's your transmission bandwidth. 2 times delta f plus 2 fm. But when you increase the modulation index, delta f, not delta f, fm becomes very small because see here this gap is fm, right? And this fm is getting small. So eventually this fm is going to be very, very small. So bt is the same as a 2 delta f plus 2 fm, but this 2 fm is very small. So therefore, bt is going to be almost the same as 2 delta f. So therefore, going back here in this graph, bt is almost the same as a 2 delta f. So if you do, if you divide bt, if you do the bt divided by delta f, this value approaches to 2 when the modulation index is getting higher. When you generate the FM waves, there are 2 different ways, direct method and indirect method. And we discussed the indirect method earlier, right? And how to do that is you first put your message into a narrowband FM modulator, okay? And using this narrowband modulated signal, put this one into the frequency multiplier in order to get the wideband FM. So we learned the frequency multiplier like this, right? And what this is that this is a memoryless nonlinear device. What does this mean, memoryless? You see this memoryless many times in many different blocks. So what this means is, what is a memory? Memory is something that you put some value in, and if there's a memory inside the box, right, then this value will stay inside the box. And this value will come out much later. Because it has a memory, it holds the value, right? And it goes into the output maybe much later. That's the memory. Okay? But memoryless means you put a certain input and you're going to get the output right away. There's no memory. So this block cannot hold the value. You cannot store the value. Okay? That's what that means, a memoryless. But in this case, it's a nonlinear device. So what that means is you are putting some value in, you are creating square, the cube, and all this different value as an output. So your output has a multiple component, but there's no memory. So you put some value in, you get a bunch of outputs, but there's no memory. That's what they mean. Okay? That's what they mean as a memoryless nonlinear device. And this is the characteristic of input and output. So your input is ST, your output is going to be VT. And when you put the ST as an input, now your input is going to be multiplied by A1. So if you only have this one, it's going to be linear. However, you have other terms, right? Your input also goes into square and then multiply into yeah, I think this is A2, right? I forgot to correct that. And S square, S cube, and S to the power n. So this ST input goes through all these different polynomial terms, and then your output has a multiple frequency, multiple component. And if the ST, our input, is a frequency, let's say in some FM, for example, yeah, something like FM. Let's say the ST is a sinusoidal function with the frequency FM. In that case, you're going to get the same frequency FM at the output, but when you go here, it's going to be cosine FM square, so you're going to get the 2 FM as a frequency, 3 FM, 4 FM. So you're going to get all different, like FM, 2 FM, 3 FM, all different multiple over FM. Okay? You get all different frequencies. We call that as a harmonics. You should get only FM because that's what we put in as an input. Our input has only one frequency, FM, but your output has the bunch of other frequencies, FM, 2 FM, 3 FM, 4 FM, all these harmonics. Just remember the word harmonics. Okay? That's very fundamental and very important words, harmonics. Whenever you hear harmonics, that basically means that your fundamental frequency is FM or F1, and the output you're going to get is a multiple of the fundamental frequencies, like F1, 2F1, 3F1, something like that. That's all we call that as harmonics. In this case, you're going to get harmonics as the output. So because of this relationship between the input and output, we know that this is a nonlinear device. But in this case, as you see, there's no memory, right? How do you know? Because you see here, whenever you get the time t, you get the output time t. So there's nothing like a t plus t minus 1, t minus 2, something like this, right? If you have a memory, that basically means if this block has a memory, then the relationship is going to be like st and s squared t minus 1 and t plus t minus 3, something like that, right? If you have such kind of thing, that means there is a memory. But in this case, everything is just a function of just t. There's nothing like t minus 1, right? So this one is memoryless. As soon as you get input, you get output. But your output has a multiple frequencies, multiple harmonics. Okay? So that's the relationship of your frequency multiplier, right? Yeah, so you basically get this kind of narrowband signal and put that into the frequency multiplier. Now you're going to get the output, but your output has all the harmonics. And by doing that, you are now making a wideband FM signals. Because in wideband FM, let's go back here. As you can see, in wideband FM, this is a wideband FM, right? In wideband FM, as you can see in this figure, the middle one here is FC. This one FC plus FM, FC plus 2 FM, FC plus 3 FM, right? This is FC minus FM, minus 2 FM, minus 3 FM. So you have all the harmonics in this case, all different harmonics, right? So you need to make all these harmonics in wideband FM. So how do you make it? As I said earlier, first you need to make a narrowband FM. Once you make a narrowband FM, you're going to get only FC plus FM, FC minus FM, only 2. And put those things into the frequency multiplier. Now the frequency multiplier make all the harmonics by this relationship, right? So that's how you make the wideband FM. Okay, now so far what we discussed is how to generate FM signal. And you are going to generate the FM signal as we discussed and then transmit. Now at the receiver, we are receiving the FM signal, FM modulated signal, and we need to do demodulate of the transmitted signal in order to get, to recover your message. Typically, there are 2 different methods for frequency demodulation. Okay, remember demodulation is what you do at the receiver, right? Modulation is what you do at the transmitter. You need to do demodulation at the receiver. So we are talking about receiver right now. Okay? At the receiver, there are 2 different methods. One is frequency discriminator. Second is phase lock loop. Okay? So let's talk about one by one. So first one is a little bit easier. So let's discuss the first one first. Frequency discriminator. Simply speaking, frequency discriminator is a slope detection followed by envelope detector. So we know the envelope detector, right? We learned that when we discussed the DC added amplitude modulation. We learned the envelope detector. So we're going to use the same thing here. But we also use the slope detection, which is like this. Okay, so let's take a look at it here. This is the frequency discriminator. So we start from this ST. This is our FM signal. Okay, so at the transmitter, we already did frequency modulation at the transmitter. So we transmitted this frequency modulated signal. So this is a signal over the air. Okay, this is FM signal. Now at the receiver, you receive this signal. And then what do you need to do? You receive this signal and you want to recover this one. We want to get this out. That's our goal, right? So demodulation in this case means that we want to get this. But this is what we receive. Okay, ST is what we receive. From this ST, we want to get M tau back. So what is the easiest way to do it? We received this. We want to recover this. So what is the easy way? Differentiation is a very easy way, mathematically. Why? Because your message is part of the phase here, right? So what you need to do is once you take the differentiation, once you take the derivative of this whole thing with respect to time, now then this one comes back, comes out. So I'll tell you why. Let me see here. Remember that when we discussed the frequency modulation earlier, okay, let's go back one step. So let's start from here. You know that this is a carrier, right? This is carrier, our original carrier. And when we discussed the FM modulation, not demodulation, modulation, what we discussed is that we want to put the message into the frequency part, right? So to do that, at that time, what we did was FC plus we did it this way. Remember that? So this one was our frequency. Your carrier frequency FC. But now we want to do FM here, frequency modulation. So your message should go to the frequency. So your message now becomes a part of your frequency, like this, right? And remember, once you do that, now we can expand it into two different terms. And then we see this MT times T. And I told you that this one is conceptually, this one is the same as integration, right? Remember that? So yeah, that's what we discussed, right? So original equation is this. This is our starting point. So that's what you transmit over the air. Now this becomes ST. Because we already put the message into the frequency part, we already have done the frequency modulation. So this is the signal we are transmitting over the air. Now we receive this at the receiver. We want to recover this message. So easiest way to do it is this one is still part of your T multiplied by T. So easy way to do it is we want to take a derivative like that as a function of T, with respect to T. Once you do that, let's take a derivative of this one with respect to T. Then this whole thing pops out, right? Because you take the derivative. So now this whole thing pops out, and cosine becomes minus sign, right? So AC, here put the minus sign, and this one here. Okay, so that's what we get. Once you take a derivative of your transmitted signal ST with respect to T, now you're going to get this. Simple, right? Once you do that, once you take a derivative, now what you can see now is that we want to recover message, right? Message. But now our message becomes a amplitude. Now our message originally in FM modulated signal, our message was inside the frequency. But since we take a derivative, now our message pops out and now becomes the part of the amplitude, right? Still we have a sign here, but you now have a message out here as an amplitude. So that's the important thing here. So again, this is a transmitted signal. This is FM modulated signal. But once you take a derivative of ft with respect to time, now then this whole thing pops out and cosine becomes a sine. Okay? And then we're going to get this. So important thing about this equation is that your message is now not inside the cosine or sine, but your message is outside as an amplitude. That's the important thing. Because you already take the derivative, your message is out. So it's a part of your amplitude. Okay? So this is our signal after you take a derivative. Okay? So after that, now what we need to do is that we are going to make this kind of slope circuit. This is what we call a slope circuit. Why? Because it has a slope like that. Okay, that's a slope circuit. But simply speaking, right? Once you do this, now your message is out, and message now becomes a part of your amplitude, and we want to recover this. So how would you do that? How can you do that? How can you recover this? Okay, let me ask you this question. Let's go back, all the way back to our previous DC added modulation, amplitude modulation. Okay, let's go all the way back to the DC added amplitude modulation. At that time, what we did was we make something like this. We make something like this, remember? That was our modulated signal. Something like that, right? We had at that time we have a carrier, but our message goes into the amplitude. But not just amplitude, but you are adding DC. Okay? So you make this kind of signal at that time. So your message is at the outside of your cosine at that time. So your message was in amplitude. So how did you recover this? Envelope detector. Then why do you add DC? Because you want to make it always positive. Compare this equation with this. It's almost the same, right? Only difference is that this one looks a little bit complex and sine, but that one doesn't matter. Here also has a cosine, but doesn't matter. What is important here is this part. Look at this part. This one is like a FC plus KFMT. So it looks almost the same, right? Almost the same. We have two terms. Here also you have two terms. And message is in the amplitude. So once you take the derivative and you get this, now what you need to do is you're going to take advantage of slope circuit like this. And then you go through the envelope detector. Same way as the DC added amplitude modulation. Then you can recover that. So that's what we're going to discuss. Here, we call this one as a slope circuit. And what this slope circuit does is your message, your signal, this signal, has your own bandwidth. Transmission bandwidth, that's BT. From here to here, that is our transmission bandwidth. Within this transmission bandwidth, we are making a unit slope like this. Okay? That's a slope circuit. And the middle point is your carrier frequency FC. Okay? So what that means is, what is a frequency modulation? What is a frequency modulation? What that means is, depending on your message, sometimes you transmit a little bit low frequency, sometimes higher frequency. So your frequency changes, right? Because your message goes into the frequency. Now in this case, your signal has a different frequency depending on your message. So put that in here. This is a carrier frequency FC. But sometimes you transmit a little bit lower frequency. Sometimes you transmit a little bit higher frequency. So your frequency changes depending on your message, right? Simply speaking, let me draw the slope circuit. So that is your slope circuit. That's what you see here, right here, right? Your signal, this kind of signal has a different frequencies depending on the message. So sometimes you have, let's say this is a time domain. So let's say your message looks like this. Then sometimes your message has a little bit higher value, a little bit lower value. So at that time, your frequency is a little bit lower than FC. But sometimes your message is high, message has a higher value, so the frequency you transmit is higher than FC. So your frequency changes depending on your message. Now sometimes, let's say your message is here, then at that time you have this frequency. Okay? So when you get this frequency and put this one into this slope circuit, now you're going to get this output. If you have a different message at different time, let's say you get this message, then you're going to have this kind of frequency. Once you have this frequency and put that into the slope circuit, now you're going to get different output, right? So if your frequency changes, your output also changes, right? Because this is a linear curve. You see what I'm saying? Because your message, depending on your message, this FM signal will create a different frequency. Okay? So put this signal into the slope circuit. Now the output of the slope circuit, you're going to have the same fluctuation. Message moves this way. The output of the unit slope has the same way, like that, right? You're going to get the same message, same output at the slope circuit. That's the intention. That's what you want to do. Because why do we need that? Simply speaking, right? we need to change this. This is still frequency thing, right? We want to change this into envelope, right? We need to change this into envelope and then put this signal into the envelope detector. Eventually, we want to use the envelope detector like this, right? But to do that, we need to change this into envelope. This is what we do. We have since this is a frequency modulated signal, your signal has a different frequency depending on the message. Okay? So frequency changes. Frequency changes something like this, right? And put that signal into the unit slope or slope circuit. Now the slope circuit will create amplitude change. Okay? So changing this frequency change into the amplitude change. Now once you get the amplitude change, we're going to put that signal into the envelope detector. The envelope detector will detect the envelope. That's our message. Okay? So that's what we do here. So mathematically, this is a slope circuit. That's a slope circuit. But it's a little bit, not easy to see it. So you can look at this figure. So visually, this is what the slope circuit does. This is a slope circuit, and this is the mathematics of the slope circuit. We have some more detailed equations here. And to go into a little bit detail, what we need to look at is complex baseband representation. But I think we probably have a chance to talk about this maybe in a couple of weeks, because the talking about complex baseband representation probably takes a little bit of time. So let me talk about this one maybe in a couple of weeks. So let me just briefly discuss this one. So what we are trying to do here is, let's go back here. In this slope circuit, now you can see that this is not baseband. What is baseband? Baseband is the frequency range of your original signal, meaning the frequency around the DC. Okay, we have a zero frequency, right? DC. So your signal always starts from baseband, like around the DC frequency, right? That's a baseband. Now you do you make your own signal in the baseband, and before you transmit over the air, you do the modulation and change it into passband. So this is a baseband. Here is a passband. And in the passband always your signal is around the carrier frequency. Baseband is always around DC, frequency 0. But in passband, your signal is always around carrier frequency, FC. So this is a passband. Because what we are talking about is frequency discriminator or demodulator. So eventually you are receiving a passband signal. That's what you transmit, and that's what you receive. That's a passband signal. Now what we need to do is in this case, we are going to just process it as a passband. That's one way. And second way is you're going to do demodulate and change the passband signal into the baseband first and then process. So we have two different ways. So this circuit, slope circuit, shows you the first way. You are not changing into the baseband. You just do process in the passband. Okay? You receive a passband signal and just process everything at the passband. Then in order to do that, you need to make this kind of slope circuit. But second way is you convert the passband signal into the baseband and do the rest of the processing at the baseband. So to do that, you need to know the complex baseband representation. That's why we talk about baseband representation. But I'll talk about that maybe in a couple of weeks. So simple message here is we are going to make a slope circuit, but you see the tilde here, right? Tilde, 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 everything tilde. In the previous slide, no tilde. There's no tilde. But in the next slide, you have a tilde everywhere. So what this tilde means is the S tilde T or SF tilde, this is all baseband. So in the previous no tilde one, that's a passband signal. But this is a baseband. So in order to differentiate, in order to distinguish passband signal with the baseband signal, now in the baseband signal we put a tilde. But this case, the baseband signal is not real. It's a complex baseband signal. So that's why it's a little bit difficult. But anyway, so that's the difference. So this slope circuit right here is a baseband slope circuit. So that's why you see tilde. So what that means is what we see here is a slope circuit at passband. Why? Because it's around the carrier frequency. So this is passband. But when you draw the baseband slope circuit, it's going to be like this. It's around the DC. So that's a baseband slope circuit. And this slope circuit is a baseband slope circuit because you see tilde here, right? So this H tilde F is this one, baseband slope circuit. But in the picture previous slide, this one is just H1F, no tilde, right? No tilde, H1F. So this one is a passband slope circuit, this one. Okay, so this one is H1F. This one is H1 tilde F. That's a passband. So that's the picture here. So what we have in this block diagram here is baseband slope circuit, H1 tilde. So that looks like this, right here. And if you look at here, right here, H1F, this is the mathematics of your baseband slope circuit. See here? There's no FC, right? In this case, there's no FC. But going back to the previous slide, this is the slope circuit at the passband. So that's why you see FC right here, right? This is FC. So that is a difference between those two. So now, simply speaking, we have this kind of complex baseband signal. Put this one into the slope circuit, baseband slope circuit. Now you're going to get the output, right? But when you do that, we know that put this time domain S tilde t, this one has H1 t, and you do the convolution of these two, that's what you get as an output, S1 t. Put it another way, if you look at it in the frequency domain, now your input signal is SF tilde. This slope circuit has its own frequency response of H1F tilde. So your output is going to be multiplication of these two. So that's why you're going to get the multiplication of these two, and you're going to get this output. So that's the S1 tilde F, but S1 tilde F is the output of your slope circuit. Okay, so that's the output. Now let me move forward. So when you look at this output right here, we have two terms. The first term is a J pi F, and second term is a J pi 1 over 2 BT. Okay, we have two terms. But first term, J 2 pi F SF, that is the same as, this is a frequency domain. So when you do the inverse Fourier transform, the frequency domain J2 pi f is the same as time derivative in time domain. So these two are actually same in the Fourier transform relationship. So this is a frequency domain we have here. This is the output of the slope circuit at the frequency domain. We can take an inverse Fourier transform of this, then you're going to get this one is the output. So both are same. So this is just time, and the previous one is just frequency. So this is a time domain. So that is our output after the slope circuit. So that's our output. Okay? That is going to be our output. So now put this S1 t tilde t back to this one. So let's look at this relationship. Our S1t, what is S1t? This is again passband because there's no tilde here, right? Passband equals to the real component of this one. This is S1 tilde, this is a baseband times carrier. Okay? Do you remember that we see this kind of equation earlier? Maybe in last week or previous week, we look at this kind of similar equation, right? At that time, the reason we introduced this kind of equation was that if you do this, right, S1t is the passband signal. And passband signal always has a carrier, right? Before you transmit, you probably put it into a carrier. So passband signal always has a carrier. And what we want to do is we want to separate carrier and our message. So that's what you do here. This is our passband signal. This passband signal is actually, there's a carrier part and there's a non-carrier part. There's a message part. And the pure message part is going to be S1 tilde t. And just carrier is going to be here, the rest of the 2 pi fct. That's a carrier part. Okay? And put that together, now you get the passband signal. That's the relationship between the S1 tilde and S1. Okay? So here what we discuss is S1 tilde, only the message part, baseband signal, and put that back into here in order to get this passband. Now once you get the passband signal, we know that we get eventually this signal. Now once you get this signal here, very long signal, right? Very long equation. Once you get this equation, now everything is clear. What is clear? Cosine 2 pi fct something something. This is just a cosine with the carrier signal. So this one is same as this. This part is same as this, right? We have some phase. Here we have some bunch of phase, but doesn't matter. Phase doesn't matter in this case, right? You have some, anyway it's cosine. Cosine something something something, but still it's a cosine. So you have a cosine, same as this one. Now, right here, you see the red one envelope. This one now is the same as envelope, which is this one. So once you put this original ST, original message, into the slope circuit, now you're going to get this as envelope. So that was what that was our intention. We want to recover this part as an envelope. So once you get this as an envelope, now look at the equation. This equation actually looks almost the same as this one, right? Almost the same as our previous DC added amplitude modulation. Look at here. We have a 1/2 pi ACBT, but this is a constant anyway, right? Each of them is a constant. So forget this. Forget this one. This is constant anyway. 1 plus some other constant times MT. That's exactly same as this, right? 1 plus some constant Ka times MT. So this one and that one exactly same. Okay? That's the message. So once you go through all these different, difficult equation, eventually we get this one. Now what is the next step to do? Put this signal into envelope detector. Okay? Same as what we did before. We did that before, right? We put this signal into envelope detector. Then you're going to get MT back. Same here. Once you get here, put this thing into the envelope detector, we can recover MT. So that is the simple message. So put that message into here. This one is one example of how to draw the block diagram of the receiver. Actually, go back here. In the previous DC added amplitude modulation, right? What we did was when you put this signal into the envelope detector, now the envelope detector recovers this because this is envelope. This whole thing is envelope, right? So envelope detector recovers this whole thing. And what did you do next? You do -1. You need to remove the DC. But in this case, you can pretty much do the same thing, but this is another way. Okay? So what you do in this case is that you can make a positive slope circuit, and you can also make a negative slope circuit. So you can make two different hardware. And positive slope circuit means this is a positive. You see that this is a positive circuit, right? Positive slope. And negative slope circuit means this one. This is a negative slope, right? You can also make this kind of circuit. So two different circuits. Once you do that, you're going to get this one as an output from the positive circuit. Where do you get this? Where do you get this? This one here, right? So this is our ST. So put this ST into the envelope detector, then envelope detector will detect envelope. And this is the envelope, right? So all the cosine will be gone. So envelope detector will detect this envelope, and this envelope looks like 1 plus MT, 1 plus constant MT. So you're going to get this after the envelope detector. However, you can, that's the case of positive slope. You can also make a negative slope. What that means is you can make this right here as a minus. So here, it becomes minus, like this, minus. That's a negative slope right here. So you can make a negative right here. You can make a negative slope. Once you do that, you're going to get this output, of course, right? This is going to be the envelope, okay, envelope, after you do negative slope circuit. So you are going to use two different output, two different slope circuits, one positive, the other one negative slope, and put your FM signal at the both sides. And the output from the positive slope circuit is going to be this one. Output from the negative slope circuit is going to be this one. And why do you do that? The reason you want to do that is after you get these two outputs, what you want to do is you want to do this one minus this. See that this is a V1, this is V2, V1 minus V2. Once you do that, then what happened? Your DC term will be gone. So the reason that you put positive circuit, negative circuit is because that this is an easier way to do DC removal. You need to remove the DC, right? Eventually you need to remove the DC. Okay, so this is one way to do it. Rather than remove the DC, you can actually go through the positive slope circuit, negative slope circuit, and later you are doing minus. Okay? Then you can easily get VT. You can easily get this one, the second one. Right? So that's what you have here. Positive. So simply, you have your FM modulated signal. Put this one into the slope circuit, right? Then you're gonna get right here after this slope circuit, right here. What do you get? You're gonna get this signal, right here. So put this signal into the envelope detector now, right? Then you're gonna recover envelope. And what is the envelope? This is the envelope from the positive slope circuit. Same thing for the negative slope circuit. You put the original modulated signal ST into the negative slope circuit. You're going to get the equation and put that into the envelope detector. Now you're going to get the envelope of V2T, which is this one. Okay? So you're going to get V1T here, right here, this one here. This V2T right here. And you are eventually calculating V1T minus V2T. This one minus this one. Then simply you're going to recover MT. Okay, that's what we call as a frequency discriminator. Because we are discriminating at the frequency, we are all dealing with the frequency, right? So putting your message, your original message is inside the frequency. By taking derivative, bring the message out. Okay? Bring the message out, and then once you do that, the message becomes part of your envelope. Put your message into the slope circuit. So the reason is your frequency change now becomes the amplitude change or envelope change, and then put this into the envelope detector, you recover envelope. That's how you recover MT. So that's the frequency discriminator. Okay? Does it make sense? Okay. Now the second method is a phase lock loop. Okay, this is a very important one. I would say this is more popular, and this is more general. You can use this one in any kind of circuit with the phase change and frequency change. So let's discuss this PLL. We call this a PLL. Let's discuss the PLL. Simply speaking, PLL looks like this. This is a simple block diagram of PLL. PLL circuit has the mainly two components. Maybe you can say three, including multiplier. One is VCO, or voltage controlled oscillator. This is the most important thing. Okay? The very important thing of a VCO, voltage controlled oscillator. We have seen this before, right? Voltage controlled oscillator. Where did you see that? Costas receiver. And what was the reason of Costas receiver? You are trying to change the phase, right? You are trying to update the phase. Eventually, your phase becomes zero, right? So that's where we use the VCO. Same VCO here, same thing. So we have a VCO. Second important thing is loop filter. But this loop filter is almost same as a low pass filter. Okay? So we have a filter. And the third thing is multiplier. But this multiplier is just same multiplier we use all the time. So we have a multiplier. So the most important thing is a voltage control oscillator in this PLL. Okay? So we have three different major components. So we already discussed the VCO, but just to give you an update, just remind you what it is. VCO, voltage control oscillator, generally how to work is you are putting the voltage. Okay, input is the voltage. Output is going to be frequency. Okay, so you put an input as a voltage, output is going to be frequency. So if you change the input voltage, your output frequency is also changed. Okay? So we always has a fundamental frequency in VCO. So if you have no input, or if you put a certain reference input voltage, then this VCO is already programmed to give make some reference, some fundamental frequency. So this one has a fundamental frequency. Okay? And now, if you have a little bit higher voltage in, you're gonna get a different frequency, or low voltage, another frequency, another lower frequency. Okay? So that's how the VCO works. Okay? Okay. Now let's take a look at here. We have ST. This is an incoming FM wave. This is ST equals to AC sine. Okay, and then our phi one is gonna be like this. Okay, it's gonna look like this. Now, when you use this one and FM wave produced by VCO, when you use a VCO, VCO will create this kind of signal. So what is RT? RT is the output of the VCO. So VCO has the input VT. VT is the input to the VCO. RT is the output to the VCO. So that's this relationship. Okay. So this relationship here, right here, looks almost the same as FM. So the PLL, actually VCO, right here inside the VCO, what happened is almost the same as FM modulation. So putting it another way, we learned FM modulation, right? We learned FM modulation. And in FM modulation, let's go all the way back. In FM modulation, what you do is we have our own message empty and put that into the frequency. Then eventually what happens is you're going to get this signal. Okay, that's the output of FM modulation, right? So when you look at this carefully, then your message is inside the integral. You have a cosine. That's going to be your output of FM modulation. Now let's go all the way to VCO. This VCO has the input VT and output RT. And let's look at this input-output relationship of this VCO. This VCO has the same relationship. This is the output of VCO. VCO output is going to be cosine 2 pi f ct plus this. And this one actually is almost the same relationship, right? Now think about this VT, V tau as an MT. Now this RT is the same as ST. In that case, this one exactly same as FM modulation. So simple message here is VCO, what happens inside the VCO is the same as FM modulation. Okay? What happens inside the VCO is FM modulation. So put this V tau as an input and put that into the VCO, and you are going to get this output. But this output actually is FM. Why is that? Simply speaking, why is that? So what I just said is, this one looks almost the same as FM modulation. Why is that? That's very straightforward, because now think about here. What is the FM modulation in general? FM modulation, the frequency modulation, you have your message, right? your message looks like voltage, up and down, like that, right? That's your message, voltage. Put your message into the FM modulation. Your output, ST, has a different frequency, right? Because this is FM modulation. Depending on your message, your output frequency changes. That's exactly what happened here. You put a different voltage, you have a different frequency output, right? So this one actually has the same operation as original FM modulation. And even the equation looks almost the same, right? So that's what happened here. And inside here, what we also can see is this FM signal ST has a cosine here, because this one is a passband signal. You have a carrier component. So this one is something cosine, right? And now what we are multiplying is another frequency, because we are creating frequency right here. VCO output is a frequency. So this one also is like a sine. Actually, this VCO make a sine, because here you see the VCO output has a 90-degree phase shift. Okay, inside here we have a phase shift. So this one actually creates a sine. This is cosine, or maybe this is sine, this is cosine. Either way, so we have a 90-degree phase shift. So what happened inside here is you are multiplying cosine with sine. So when you look at the output here, ET, when you look at the output, right here, what we see is we see cosine times sine. Okay, we see the cosine frequency with the sine frequency. We are multiplying two different frequencies. So whenever we see cosine times sine, what we did was we always see cosine 2 pi fct and sine 2 pi fct plus phi, something like that, right? We see this many times. And what's the next step to do all the time? We just change into sine 4 pi fct plus phi plus another sine phi. That's what we did all the time, right? Same thing, exactly same thing happens here. Right here, we have a cosine and sine, we multiply. So right here, after multiplication, we see this, cosine times sine. Okay? So using this identity, we can change this into high frequency component with the DC frequency, DC component. That's why we need low pass filter. Okay? That's why we have a low pass filter. Why do we have low pass filter? Because we want to kill this guy. Okay, we want to remove this guy, right? Because we want only this guy. That's what we want. We did that all the time, right? Whenever you do mixing, or whenever you do the multiplication of two different frequencies, we always has a filter. Okay, always. When you multiply two different frequencies, you always have a filter right after that. Same here, right? You always has a filter. This is the low pass filter, because we want to remove the high frequency component, so we have a filter. Once you have a filter, what is the output? Here output, you have this DC component only. Okay? And that DC component here is some value, right? Like some 0.1 or something like that. So that value is going to be the output here. And that output is again going back to the VCO. Okay? And then you are going to have a different frequency out. And that different frequency is multiplied again, okay? And then create the different output here. And again, the high frequency component is removed. You're going to get another value. And that other value is again going back. It's like looping. And eventually, once you do looping, your error component, this is actually error component. That's why we say ET. This error component is getting small and small. Eventually, your phase is going to be matched. Or frequency your phases match or frequency match, right? So that's the intention of PLL. So that's why once it matches, then we call it as a locked. So that's why we call the phase locked loop. Okay. Once this feedback changes little by little, and the phase is matched, okay, phase match, we call that as a locked. So phase is this loop is gonna lock the phase at that point. So that's why we call it phase lock loop.